it's given the period of oscillation of a simple pendulum has been found 5 times and the 5 values have been given. So we have to find the average absolute error. Now the method to do this is we have to find delta x, which is the average absolute error. So this will be so delta x1. So let me write down the formula first and then I'll explain what does this mean. So since there are 5 experimental values which have been mentioned, so we write the delta x value for each of them and we divide the sum by 5. Now delta x1 stands for how much does the experimental value differ from the average. So we take the mod and x1 minus x bar. Now x bar stands for the average value. So if I try to find the average value, since all of the 5 values are given, so we will find the sum and then divide it by 5. So let's add all the values. So 2.63 plus 2.56 plus 2.42 plus 2.71 plus 2.80 divided by 5. So if we solve for this, we'll get 2.62 seconds. So this is the value of the average period of oscillation. So let's find out delta x1 mod of, now the experimental value first is 2.63 minus we take the average, which is 2.62. This will give us 0.01. Similarly, let's find delta x2, that will be mod of x2 minus the average. Now x2 is 2.56 minus 2.62, which is the average, and that will be equal to 0.06 seconds. Similarly, we can find out the delta x3 all the way up to 5. So delta x3 can be found out as 0.0, delta x4 would give you 0.09, and delta x5 would be 0.18. Now if we add all of these values, the total sum would be equal to 0.54. So the total absolute average error, that will be given by this sum divided by 5. So this will be 0.108. So we can approximate that to 0.11 seconds. Let's see if any of this matches the answer options. So 0.11 seconds, hence option B is the right answer. Next is question 16, which only Ayush has attempted correctly. So let's see how to solve this problem. Question number 16. So in this question, the weight of a material in air is given and its weight is given in water. So using these values, we have to find the relative density along with the maximum percentage error. Now the formula for relative density, that is given by the weight of the material in the air, so that is the numerator, divided by the weight loss due to water. So let me symbolize this. Relative density is weight in the air divided by the weight loss due to the water. So the total weight of this material in the air is 5 and weight in the water is 4, which means the weight loss would be 5 minus 4, which is 1 newtons. Now the weight of the material in air is 5 newtons. So the absolute value for the relative density would be 5 over 1, which is 5 newtons. Now we need to find the maximum possible percentage error. So since the formula is this, so to find the percentage error for the relative density, so we can write this as delta WA by WA plus delta WL divided by WL into 100. Now delta WA is the absolute uncertainty in the measurement of the weight in the air, which is given as 0.05 newtons. So this would be 0.05 divided by weight in the air is 5. Delta WL stands for the uncertainty in the measurement of weight loss divided by the weight loss. Now this WL is already found out as 1 Newton, so the denominator we can write but this delta WL is a little tricky to find. You need to be aware of the formula first. So let's revise that particular formula which we have done in the class. Let's say if a parameter is given as a sum, if x is equal to a plus b or x is equal to a minus b. In either of these cases, if delta x is the uncertainty in the measurement of x, this will be given as just delta a plus delta b. Now the sign between the two a and b could be plus and minus, but when it comes to uncertainty, the plus sign is only taken. Now in the formula for weight loss, this is equal to the weight in the air minus the weight in the water. So if we see just the uncertainty, so delta WL, that will be delta W air plus delta W water. So if we scroll up to find out the weights, so the weight has been given 5 plus 0.05, so 0.05 is the delta W air and this 0.05 is delta W water, which means both of these values are 0.05. 0.05 plus 0.05, so this will give us value 0.1. Hence we can put delta WL as 0.1 in this particular spot. So if we solve for this entire expression, we get 1 plus 10, which is equal to 11%. Hence 11% is the maximum possible percentage error in the measurement of relative density. So let's see what is the answer option. Since the actual value was 5 newtons and the percentage error is 11%, so hence option number A, that is the answer. Next is question number 17, which all of you but Vaibhav has done correctly. So let's see. Okay, Vaibhav, I guess you might have done an error in the formula, otherwise this is a simple question. So we have to find the maximum percentage error in the density. For that we need the formula. Density rho can be written as mass divided by volume, and a wire is given of length and radius, which means we can consider this as a cylinder. Now the cylinder volume is given by this formula pi r square L. Now to find the maximum percentage error in the density, the formula goes like this. So delta m divided by m plus 2 times delta r divided by r plus delta L by L into 100. Delta m is the uncertainty in the measurement of mass, which is 0.003 grams, divided by mass, which is 0.3, plus 2 times delta r is 0.005 over the value of radius, which is 0.5, plus delta L, which is 0.06, divided by 6 multiplied by 100. Now if you solve for the entire expression, you will get the answer as 4. Hence the maximum uncertainty in the measurement of density is 4, hence option number A. Next is question number 18. So in this particular question, a ball is thrown in the air and 5 different students are individually measuring the time it takes to fall back down using stopwatches, and since there are 5 students, so they will get 5 values. We have to find out what is the uncertainty in the measurement of these results. So the formula for uncertainty is this. Uncertainty is given by, so first of all you have to find the range and divide that by 2. Now what do we mean by range? Range means the difference between the maximum and the minimum values. So if you observe all these values, the maximum out of this is 6.4 and the minimum is 5.8. So if we subtract, we find the difference and we divide that by 2. So we'll get 0.6 divided by 2, which is 0.3 seconds, which means the uncertainty in the measurement of this time, that is 0.3. Now part B is, how should the resulting time be expressed? So the answer would be x bar plus minus delta x. X bar stands for the average value of time. So how do we find that out? We will find the sum of all the times, which is 6.2 plus 6 plus 6.4 plus 6.1 plus 5.8 Now if we divide the entire thing by 5, the average would come out to be 6.1. So the resulting time can be expressed like this: 6.1 plus minus the absolute uncertainty, which is 0.3 seconds. So this is the answer to part B. Next is question number 19. So here we have to find about the speed of the bullet. So it's given the distance traveled by the bullet as well as the time. Now the speed is nothing but distance over time. Now if I see the distance is 154 and the time is 0.4 seconds. So 154 divided by 0.4, that will give us 385 meters per second. So this is the speed of the bullet. Now we have to consider the uncertainties involved in this particular question. So first part is calculate the fractional uncertainty for the speed of the bullet. Fractional uncertainty means we need to find delta V over V. Now as we can see, this formula of speed, which is distance over time, using this we can write, let's say if the speed is V, so delta V over V would be delta D divided by D plus delta T by T. Now if delta D, so delta D is the uncertainty in the measurement of distance, which is 0.5, we divide that by 154, plus delta T is the uncertainty in the measurement of time, which is 0.05 seconds, divided by 0.4. Now so this is the total fractional uncertainty in the speed of the bullet. So if we solve for this, we will get 0.12825 and we can approximate this to 0.13. So this is the fractional uncertainty, or the answer to part A. Part B states we have to find out the percentage uncertainty. Percentage uncertainty is nothing but the fractional uncertainty, multiply that by 100. So 13% is the percentage uncertainty. Part C is we have to write down the speed of the bullet using the absolute uncertainty. This is the key word here. So the speed of the bullet would be 385, which we already found out, plus minus the absolute uncertainty. Now since the fractional uncertainty was 0.13, so let me write that down. Delta V over V is 0.13, where delta V stands for the absolute uncertainty. So that can be written as 0.13 times V. V is 385. So if we solve for this calculation, we will get approximately 50. So delta V, so 50 is the absolute uncertainty in the measurement of the speed or velocity. So if we put the value of delta V in this, so this is the answer to part C. This is how we express the speed of the bullet using the absolute uncertainty, which is 50 meters per second. So this is the last question. So the formula itself is given to you, power in terms of current and resistance. So power is I square R. So the first part is we have to write down the value of the supplied power correct to the significant figure. So this is nothing, we have to just use the formula, power is equal to I square R. Now current is 3 amperes multiplied by the resistance, which is 13 ohms. So if we solve for this, we will get 117 watts. Now what is the unit of power? So that was the answer to part A. Part B is we have to find the percentage uncertainty for the current passing through the resistor and its resistance. So the percentage uncertainty for current is expressed like this: delta I is the uncertainty in the measurement of current, which is 0.1 amperes. Divide that by the value of current into 100. So this would be 3.33%. Similarly, using the value of the resistance, we can find the uncertainty, percentage uncertainty for resistance as 0.5 divided by 13 into 100. So that will give us 3.85%. So these two are the answer to part B. Part C is we have to find the absolute uncertainty in the electrical power. For that we have to use the formula itself. Since power is equal to I square R, so delta P by P, that can be written as 2 delta I by I plus delta R by R. Now delta I by I is the fractional uncertainty in the measurement of current, So that can be written as 2 times 0.033 plus delta R by R is the fractional uncertainty for resistance, which is 0.0385. So if we solve for this, we will eventually get 0.105. Now delta P, now since this power was in the denominator, so delta P can be written like 0.105 multiplied by the value of power, which was found out as 117 watts in the part A. So if we solve for this, we will get 12.3 watts approximately, which is the absolute uncertainty in the measurement of power. This is the answer to part C.